Have you ever been to a tailgate and wondered to yourself, how long do I have until this beer is warm? Or how long would I have if I was using a koozie? Well, today I'm here to answer those questions. We're going to determine experimentally how long it takes for a beer to warm up in your hand with and without a koozie. And then we're going to do a heat transfer analysis on the problem so that based on your conditions like the outside temperature or if you're an extremely hot human being, we can predict how long you have until you should have your beer completely drunk. So I've just pulled both beers out of the fridge at 4 degrees Celsius. I've placed one in the koozie, and I'm going to use this meat thermometer at 5-minute intervals to measure the temperature of both of these beers. For the non-koozie beer, I'm going to use a piece of cloth so I can get the best reading possible. I understand that this is probably not completely accurate, but I'm hoping that if I'm consistent over the course of 90 minutes, we should be able to see the general trend. I'm going to be holding both of these beers in my hands for the duration of this 90 minutes, and I've calculated that I'm covering about 4/9 of the surface area of the can, 2/3 of the height, 2/3 of the circumference. Now, while that's going, let me explain a little bit about the heat transfer that's going on in these cans. Here's a little schematic I've drawn of the situation that we're analyzing. The first thing I did was research some of the constants, initial conditions, and dimensions of the scenario. I found that an average 12-ounce beer can was about 122 millimeters high and 66 millimeters in diameter. I also found that the average temperature of a male's palm is about 32 degrees Celsius. I used my meat thermometer to measure the temperature of the air in the room and found that to be 22.5 degrees Celsius, and I estimated that the thickness of the koozie was about 1/2 centimeter. Lastly, I've labeled a couple temperatures on my diagram that I will use in the resistance network that is to come. TH is the temperature of the hand, TK is the temperature of the koozie, TC is the temperature of the can, and TB is the temperature of the beer. I also made some assumptions to simplify this problem. I assumed that all of the properties of the beer are the same as water, as beer is 95% water. I also assumed there was no resistance in the can because it is very thin and has a very high conductivity. Lastly, I assumed there was no heat transfer at the top or bottom of the can. It helped me simplify a lot of the math, but I did drop out a large chunk of surface area. As you can see, there are two different paths heat can take to enter the beer, either from the hot hand or from the warm ambient air temperature. I drew a resistance network to model this. The top path shows how heat can enter from the ambient air. It has to convect into the koozie and then conduct through the koozie to the can. As I said earlier, I assumed there was no resistance in the can. The can is the same temperature as the beer. The path heat can take from the hand is slightly different. It has to travel from the hand to the koozie via a contact resistance, and then it has to also conduct through the koozie. Next, I jumped right into ease to begin calculating some of these resistances. I began by defining all of the dimensions, constants, and initial conditions I had assumed earlier. I approximated the conductivity of the koozie material by using Ease's substance called polystyrene beads. I also approximated the contact resistance between the hand and the can with a value I found off Google. From this, I was able to calculate some of the properties of the beer and use the Ease function for natural convection to calculate the heat transfer coefficient from the air to the koozie. I was then able to determine the convection and conduction resistances needed to develop a total resistance for each path. To see if I could use lumped capacitance to approximate the temperature of the beer, I calculated the BO number by dividing the internal resistance in the beer by the total resistance heat has to go through to get from your hand or the atmosphere to the beer. I calculated 0.12, which is very close to 0.1. I could then use this equation and calculate a tau lumped from the mass of the beer and its specific heat capacity to estimate a temperature at some time down the line. Lastly, I calculate the final temperature of the beer for a given time. To make this a more conservative estimate, I divide the final temperature by 0.8 to account for things like the top of the cans transferring heat and also some internal mixing that might speed up the heat transfer. Alright, well here's the final plot I get for the temperature of the beer versus the time it's spent warming in your hand. Let's compare that to the data I collected in real life. Alright, so here's the data I collected in real life. As you can see, it's fairly close to what we predicted with these equations, but the beer warms a little bit faster. To be honest with you, it was originally farther off, and that's why I added the correction factor. This is something that could be fixed in the future though, if you further develop the equations and reduce the number of assumptions, like accounting for the top and the bottom. I took my hands off around 9 p.m., which is why it begins going down. According to Google, beers start tasting bad around 13 degrees Celsius. So our data shows that you have about 40 minutes for a beer with a koozie or 15 minutes for a beer with no koozie until you should be finishing up that beer and getting on to the next one. Thanks for watching, and I hope this was helpful.